Okay, so today we'll talk about the last topic for the exam. It's a nice place to end the material for the first exam because it's still related to the polynomial interpolation, but it is just a different way of doing the polynomial interpolation, um, distinct from like the Lagrange interpolation approach. So just to kind of like remind you how the Lagrange interpolation worked. It is really simple, like, if you think about it, let's see, where was the example I was giving you? Right, like, so like the one we did at the end of class was like, I gave you 4 points because it's 4 points. You're trying to find 4 - 1 is 3, so a polynomial of degree 3 that passes through all the points. So again, like the first step was to construct this auxiliary function, which is just becomes 0 at each of the x coordinates that you were given. That's what I was calling L of x before. And then from this one, you kind of construct like auxiliary polynomials just by deleting one of the factors at a time, right? So you delete the first factor, the second factor, the third factor, and the fourth factor. And that's how you get like these new polynomials. That is closer to what you want, because now they vanish at all except one of the x values. The thing is that at the value where they're not 0, they may not have value 1. And having value 1 is like a useful normalization condition to have. So basically, you compute the value of each polynomial at the x value where it's not 0. So you get these numbers, and then you rescale the polynomials by that number so that now they have value 1 at those points. Okay, so basically, you found the idea here is that you find polynomials that vanish everywhere except at one of the x values, and at the value where they don't vanish, they're just 1. And then the idea is that the polynomial is just that you are after, it's just like a linear combination of these basis polynomials. In a sense, they're kind of like a basis. And so, and you just the combination factors are just the y values that you had for the points. Okay, so the construction is like pretty straightforward, but it still has some it's theoretically there is something not too pleasing about it. If you think about it from like an experimental point of view, which is like, okay, right now the way I'm doing it, the points were kind of like preordained, they were just given. But what if if you think about these points as being measurements or whatever, what if you have like an extra point that you want to add to the table? Maybe you forgot that you wanted to include this point. So it is not super clear from this presentation how the polynomial that you get by adding an extra point is related to the polynomial that we just found. So let me start just mentioning this as a drawback of, you know, so one of the disadvantages of the Lagrange interpolation is that if you add an extra point, an extra data point, let's just call it an extra data point, you know, um, like you can find a polynomial, a new polynomial. The degree increases by 1, right? Because now you have one extra data point, so that increases the degree by 1 of 1 degree higher. But it's not super clear how this new polynomial is related to the polynomial you had found before. But it's not clear to the one we had before. It's almost like you kind of have to start almost from scratch to find the polynomial again, which is not desirable, uh, not like a desirable way to construct it. So you would want something that feels a little bit more recursive, where if you have 9 points, you find a polynomial, and if you have 10 points, the new polynomial is basically the previous one plus something else. So kind of like so that it kind of like you can build up on what you had before. So we would like a way to describe the polynomial that feels more recursive. meaning that one can use the polynomial you have, one can use one that one can use the older polynomial to find the new one and add something to it to find the new one. Okay. And the way we will do this is actually basically Newton have found the way to do this. It's called like the Newton form of the interpolation polynomial. So we will discuss the Newton form of the interpolation polynomial. Okay. It's like a very elegant form. I think you kind of like appreciate it. It's like very clever. In a sense, it generalizes Taylor's expansion, which is also interesting. So we'll also discuss that in a moment. I'll explain why that's kind of like the case. Um, so first, actually, kind of like just to have like a setup in mind. Again, kind of like the data points, you can really think about them as like complete like measurement values. Um, but it's also useful to think about them as being obtained from sampling, as we talked about last week. So just that's just for psychological purposes. It's not fully like required, but it's convenient to think about it this way. So we will think that these data points are obtained from sampling. So what did that mean in practice? So what I was telling you last time is that in this case, when you are talking about sampling a function, what you have is a function y equals f of x. And you decide just to keep a finite amount of information about the function. So basically you choose some number of x values. So for example, this could be x0. By the way, they don't have to be ordered. So like just to make it clear that you don't have to order them or anything like that. So you could have x0, x1, x2, x3, up to x to the n. Again, like the points, like they can be anywhere on the number line. The only restriction on the points for now that we have worked with is that they were different x values, right? And in the case of sampling, the idea is that, well, each value for x gives you a corresponding value on the function, right? So here you get like, the corresponding point on the graph. Okay. So the point is that when you think about the values obtained from sampling, is that basically the idea is that the y values are just the values of the function evaluated at those x values. So in this case, the data points are just like x0 comma y0, x1 comma y1, x2 comma y2 up to xn comma yn. They are just the same as x0 comma f of x0, x1 comma f of x1, x2 comma f of x2, and boom, xn comma f of xn. So again, like it's kind of like more like a psychological thing that where you want to think of these y values as coming from the values of a function. Okay, it's not necessary, but it kind of like it is in practice one of the ways where it is actually used as. So it's kind of like a good thing to have in mind. The reason for that is because like it kind of like connects this problem to a problem, from Calc 2, which was like the Taylor polynomials. right? Because one way to think about the Taylor polynomial or like the Taylor approximation is that you're trying to approximate a function in terms of the f of x0 and the derivatives, right? F prime of x0, f double prime of x0, etc., etc. So in the usual Taylor approximation, right? So let me just, as a motivation of how to think about this. So here's some motivation. When you do let me just check how many integrals do I want to do here. Sorry, how many derivatives? No. Let's say the degree n, right? What, when you have a function f of x, you can approximate it using the Taylor polynomial of degree n. Center at a particular point, right? Center at x0. So the idea, as you remember, hopefully, I think we mentioned this a little bit before, right? Is that when we were talking about error estimates, the idea in the Taylor expansion is that you would say, well, f of x is like f of x0 plus f prime of x0 times x minus x0, right? Plus f double prime of x0 over 2 times x minus x0 squared, right? Dot, 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 dot. And then you continue up to the nth derivative times x minus x0 to the n over, sorry, the nth derivative at x0. Let's see if I can evaluate, put here the over n factorial, right? And of course, like that is not fully correct, right? Because like that function is not necessarily a polynomial, but there was like an error term, right? Which you can write it out in many different ways. Like one of the ways I mentioned in class that you kind of like, wait, let me just write this a little bit nicer. The point is like, this is kind of like the polynomial part, right? And then there is an error term which involves the nth plus 1 derivative at some number c. Okay. So this is, I mean, this is the one of the many versions in which you can write the leftover error term. This is not the only way by any means. The idea is that c here is a number between x and x0. So here c is some number. Okay. But but the idea is that in this approximation, right? In this approximation, the information that you need was a point and the derivatives, the first, the second, the third, the fourth, the fifth derivative up until the nth derivative, at that point, and then there's some error term, right? So here, the usual Taylor polynomial is kind of like all information at a given point, but you need a lot of information about the derivatives and higher derivatives. So in the Taylor polynomial, so what I want you to notice is that in the Taylor polynomial, you only use one point, but the kind of like the penalty for using only one point is that you use a lot of information about that point because you use the value of the function at that point, the value of the first derivative of the function, the value of the first derivative of the function of that point, and so on. But it requires a lot of information about that point, which is, f of x0, f prime of x0, f double prime of x0, and this, etc., right? So it uses like the value of the function together with the information about the derivative, the higher order derivatives of that function. Okay. So that is kind of like the, yes, sorry. Yeah. You mean like on the previous page?
Yeah.
I'm sorry, let me just like scroll down. What were you going to
You said for C, that's some number between x sub n and x zero, or just x, or just x.
Oh, sorry, between x and x0, yes.
Oh, okay, I just
Yeah, no, yeah. Right, there's no well here like right, I only have two numbers, right, which are x and x0, right? There's no x sub n. There is an nth degree derivative, right? But we're not kind of like creating a sequence or anything of that sort. So yeah. This kind of like comes from like the mean value theorem. You just have to apply the mean value theorem in clever ways. You kind of like apply it n times or n+1 times. Like, I always get wrong like the number of times, but it just comes from like a number of applications of the mean value theorem to an auxiliary function. The important thing that I want to kind of like you to notice is that these, like, the thing that is in black is a polynomial, right? It is a polynomial of degree n. Um, and then, well, of course, this is also some sort of like a polynomial part, but like it doesn't refer to the point x0. So like, you can just think about it as an error thing. Like, the important thing is like it's saying the function is approximated by some sort of like degree n polynomial plus some junk. The junk is well understood because there's a formula for it, but it doesn't matter so much right now like what the junk is. It's more like the fact philosophically that you can approximate the function by this polynomial. So the Lagrange, in a sense, like the Newton and Lagrange forms or interpolation problems are kind of like in a similar spirit. It's just that instead of like using a single point, they use n points or n+1 points, but no information about the derivatives. Just that they kind of like just so you traded one point with a lot of information about derivatives at that point with a lot of points, but only information about the values of the function at those points. So it's kind of like a trade-off. You see, it's kind of like a balancing act. So, and I'll tell you what the Newton form is. So for the Newton form of the interpolation polynomial, the goal is to find the polynomial that passes, let me just write it here. You want to find this polynomial of degree n, which passes through, as I was saying, x0, f of x0, x1, f of x1, and xn, f of xn. That polynomial already exists because it's the same one that we found with Lagrange interpolation, right? There's only one polynomial. It's just that you can write it in different ways, but there's only a single polynomial that passes through all these points of degree at most n. So this polynomial is the same from the Lagrange interpolation, right? It's just going to be expressed in a different way. So let me just say that to make it clear. This polynomial is the same to the one using Lagrange interpolation. It is just going to be written in a more suggestive way. It is just going to be written in a more suggestive way. Okay. So what is the formula? The expression that you want to try to find, and kind of what we'll do today is kind of like determine the coefficients. So the idea is that the way in the Newton version of the polynomial, the way you want to write it is to say that Pn of x, okay, it's going to be a constant C0 plus a constant C1 times x minus x0 plus a constant C2 times x minus x0 times x minus x1. Well, let me just continue here. Plus a constant C3 times x minus x0 times x minus x1 times x minus x2, dot, 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 until you get to Cn, a constant Cn, which will be x minus times x minus x0, x minus x1, dot, 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 time until x minus xn minus 1. Okay, so I need a little bit more space here. so that this doesn't look too messed up. Oops. So here, like C0, Z1, C2, C3, etc., are the coefficients that we have to find. Here, C0, C1, C2, C3, up to Cn. Oops. Ah. They are coefficients we must determine. But it kind of like gives like a familiar vibe to the Taylor polynomial, because if you look at the Taylor polynomial, it's like, what was the Taylor polynomial? It's a constant plus something times x minus x0 plus something times x minus x0 squared, right? Plus something times x minus x0 cubed. So here what we're doing is that instead of like having x minus x0 squared, x minus x0 cubed, we are kind of like splitting it up into products of factors, right? So I'll do x minus x0 times x minus x1, x minus x0 times x minus x1 times x minus x2. And so you see kind of like in the next step, you just add one extra factor involving like, and one of the other points that you were given. So it's kind of like taking this power, it's kind of like taking this power x minus x0 to the n and just kind of like breaking it into a product of like individual powers with different x values. So here, so let me just make a remark of that sort that, so, kind of like the idea is that comparing to Taylor, if you want to compare it to Taylor, notice that it is like kind of like what you're doing is like x minus, what I'm saying is that x minus x0 squared kind of like gets turned into x minus x0 times x minus x1, and then x minus x0 cubed, this one gets turned into x minus x0 times x minus x1 times x minus x2. So you see there's still, this is still quadratic, this is quadratic, this is cubic, this is cubic. It's just like they're kind of like breaking apart the factors. And then just to do one more, like x minus x0 to the 4 gets turned into x minus x0 times x minus x1 times x minus x2 times x minus x3. And so on, right? Like kind of like continues with the other powers, that same, etc. But it is kind of like a good comparison to have. Right. In fact, there's another comparison I can do with Taylor, you know, because if you look at, sorry, just to kind of like write it down here. If you call this like, the Taylor polynomial of degree n, let me just copy paste this one. So here's like another analogy to have. So here's another thing. Which you kind of like are told this in Calc too, but it's something that you kind of like come to appreciate once you kind of like start thinking more about numerical analysis and all these things. It's another thing is that if you kind of like wait, if you call this polynomial the Taylor polynomial of degree n, I'll use uppercase T for Taylor, right? If this is the Taylor like the approximation or like the Taylor polynomial of degree n, just like the way it's structured, you can see that that is the Taylor polynomial of degree n minus 1 plus an extra term, right? Like it is the same formula. Notice that this is the same as the Taylor polynomial of degree n minus 1 plus an extra factor, which is like fn of x0 over n factorial times x minus x0 to the n, right? So kind of like the Taylor polynomials have like a recursive structure, because if you have the degree 4 Taylor polynomial and you want to find the degree 5 Taylor polynomial, you just add an extra term. You don't have to redo the calculation, right? Like you can kind of like store in your computer like the memory of what was that polynomial of degree 4 and use that as useful information for like the next step. And so that's kind of like nice. And if you kind of like notice, there's something similar happening in this Newton form of the polynomial, because if you know, just to kind of like go back, something similar happens with the Newton form of the polynomial. Because if you look, let me copy paste the polynomial. Where are you? Right. If you think that this is a polynomial, if you write the polynomial in this way, that's what I mean. If you write the polynomial in this way, it is kind of like, you can kind of like see that in a sense, you know, it is clear what's happening from one step to the next, right? Like you're multiplying by a new factor, and well, you have to introduce this different concept. But it kind of like does say, well, actually, maybe I should just like write the first few examples, right? If you look at these examples, what is it? The P0 case, P0 of x would be Z0, and then P1 of x would be C0 plus C1 times x minus x0, right? And then P2 of x would be C0 plus C1 x minus x0 plus C2 times x minus x0 times x minus x1. And you could kind of like see that it kind of like is almost like a lower triangular, you can arrange it almost like as a lower triangular matrix, because, this one is kind of like P1 is just P0 plus something new, right? Plus something new, which is this degree 1 thing. And P2 is just P1 plus something new, right? So this is P1 of x plus a new thing. And it's kind of like not too hard to convince yourself that that is more or less what happens in general. So Pn of x, by writing the polynomial in this particular format, Pn of x is Pn minus 1 of x plus this constant Cn times x minus x0, x minus x1 up to x minus xm minus 1. So kind of like the thing is that this does have a more recursive structure to it, which you don't get if you write a polynomial in the Lagrange presentation. So if you try to use Lagrange interpolation to find the polynomial, it's not super clear how the next degree polynomial would be related to the previous one when you add an extra data point. Whereas here in the Newton form, you can kind of like use the previous calculation to keep building up on top of it. So that's kind of like the advantage of having the Newton version of the polynomial. That's kind of like the nice thing there. So it all boils, once we have found the coefficients, which is also very beautiful, like formula for the coefficients, it's called these divided differences. Once you have the formula for the coefficients, that's all there is to it, but it's like a much more elegant way of like writing it down. So you can use in this format, the polynomial is presented in a recursive way. The polynomials are because there are multiple ones, are presented in a recursive way, which again is important if you think about it experimentally, because imagine like, or just like for this is machine learning like algorithms, if you wanted to add like a data point to the training data, and now you have, if you had to redo things from scratch, then you just wasted millions of dollars, like you want to kind of like save progress, and this way of presenting the polynomial allows you to say, make up, not start over the problem. That's kind of like, again, like an important thing to kind of like keep in mind. Okay. So far, so good. Is that making sense? Okay, so now I'll show you. It is super easy to find the formula for what the coefficients are. So like, let's just focus on that for now. Okay. So where should I do it? I'll start here and then we'll continue like in the next page. So let's just find the coefficients. Okay, so let's do that. Okay, so again, the formula for the polynomial, right, is a Pn, right? Pn is C0 plus C1 times x minus x0, blah, 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 blah. This thing that you see there, okay? So notice that, like, every factor, like after C0, every factor after C0 has x minus x0, right? Every factor after C0 has x minus x0. So the first thing that you should do, again, this is supposed to be an equation. This is supposed to be a polynomial, so you can evaluate it at any point. So you might as well evaluate it at x0 because it's the easiest one, since basically all the factors except one would be zero, right? Like, because if you evaluate this as x0, you get x0 minus x0 here, you get x0 minus x0 here, you get x0 minus x0 here. You will get a bunch of zeros. The only one that survives is C0. So you evaluate this at evaluate it at evaluate this equation at x equals x0, and you just get that Pn of x0, right? You get that Pn of x0 would be C0, right? Okay, let's just see if everyone is okay with that. So far, so good. Is that making sense? Now, this is a again, this polynomial already exists, just to make it clear, right? Like, you can find it in many different ways. It is the same, for example, that you find with Lagrange interpolation. So this polynomial already is out there. We're just rewriting it in a different way. So we already know what this Pn of x0 is, because this is supposed to be an interpolation polynomial. So it is supposed to pass through this data point. This polynomial is supposed to pass through this data point x0 comma y0. Okay, but this polynomial passes through x0, y0. But what is y0? Because we're thinking that this comes from sampling, right? Y0 is just f of x0, because it's kind of like there's an underlying function, where this comes from. So basically, the value of the polynomial should be f of x0, because this is an interpolation polynomial. Remember, that means that it passes through it is supposed to pass through all those points that you were given. So essentially, the formula for z0 is just f of x0. And that's also how Taylor starts, right? Like, the formula for Taylor is f of x equals f of x0 plus. So you see, it kind of coincides a little bit with how Taylor begins, which is also something that I want you to keep an eye on. Okay, so we're making progress slowly but surely, right? So that is the first value, the first concept. Okay, so let me update. I'll just do like two more steps, because that kind of shows you kind of like a feeling for what's supposed to happen, and I'll tell you what happens in general. You can just kind of like prove it by induction. There are many different ways to prove, the structure that you'll see then becomes explicit if you play. But I think once you just see what happens in the first next two cases, like, it's more than enough to see what the idea is. So if you update the information of the polynomial, okay, so I'll replace C0 with f of x0. Is that okay so far so good? Okay, and now kind of like the strategy is the same in the sense that you want to evaluate this at a convenient value of x. So what would be the most convenient value? Now we already used x0, right? So what would be another useful value that you continue with in this equation? What should I plug in there? X1, right? Like, because like that's the one that kills off, right? Like X0 was the best one because it kills off all of this, but I cannot reuse X0. So I'll just use X1 because it kills all the others, right? Like, so, you're trying to kind of like simplify the most as possible. So, okay. So now we take, okay, so now take X to be X1. Okay, so you get Pn of X1, right, is f of x0 plus c1 times x1 minus x0, right? Everything else dies, right? Everything else has an x1 being subtracted, so when you plug it in at x1, it goes away. And okay, and this is similar to what we were talking about. This is a interpolation polynomial, so we already know Pn of x1. That's just f of x1 because it's supposed to pass through those points. So because of the interpolation property, this is just f of x1. So you start getting also something that hopefully starts looking a bit familiar. You get that f of x1 is f of x0 plus z1 times x1 minus x0, right? So if you solve for C1, right? What is the formula for C1? So that is the formula for C1. That looks familiar, right? Because what is that quantity appears in many places, right? It's kind of like a slope of a secant line, and it's kind of like a similar formula to the slope of a line. Also, like if you took a limit, right? Imagine taking a limit as x1 approaches x0. That is just the first derivative at x0, right? So it is kind of like a finite version of the derivative. Like that's why it's called like a finite difference, because it's kind of like a finite approximation to the derivative. So as x1 approaches x0, you would get f prime, you would get f prime of x0. So again, you see how it's generalizing Taylor's formula, because Taylor's formula is f of x0 plus f prime of x0 times x minus x0. And this is kind of like doing like a version of that, where now it's two different nodes, like that's another way to call these things. And so because it's two different nodes, it's no longer with the derivative, but more with its finite approximation. So this quantity is useful to have like a notation for it. It's called like a finite difference. So I'll because otherwise it becomes too messy to just kind of like write it down that way. So this quantity is special enough, and it's called like a finite difference. So a finite difference. So and there's a specific notation for it, which is kind of like is this one? Oops. So the notation for a finite difference is f of x, kind of like in a square bracket. You write f of x0, x1 in square brackets, and that is the same as that quantity. Okay. And something to notice, where you got that? Oh, okay. Something to notice is that, which is also useful, is that, in this case, the order does not matter. Like, because if you got put x1, x0, it's kind of like the slope of a line, right? When you compute the slope of a line, it doesn't matter which which point you subtract from the other one, it doesn't really matter. Like, the slope of the line is insensitive to which one, when you do the delta y and the delta x, the deltas are the only thing that matters. So in fact, it's kind of like, well, the technical term for that is permutation invariant, as in like if you permute the order of the list, right, like it still gives you the same value. So, but kind of like symbolically, you can write it like as f of x1 comma x0. So meaning it is insensitive to how you order them, which is kind of like also nice to have. So the finite difference, so this finite difference is insensitive to how you order x0 and x1, to how you list, let's say, list x0, x1. Okay. So we're getting there. I'll just do the next one to show you that kind of like the recursive feeling for it, because once you see how the next one comes, it is plausible what happens in the other cases. Okay, so far so good. Is it making sense? Okay, so let's update the polynomial one more time, and this is the last calculation I'll do here. Oh, by the way, so if I already posted the study guide and the kind of like also some more like practice problems. As I told you, like the exam will be mostly kind of like theoretical, as in I may ask you define this term or give a short proof of this fact. So if you look at the study guide, I tell you which proofs I expect you to know and also which definitions like you should know. Um, there might be like a problem or so like of computing something, but it would have to be a very short computation because like as I told you, like almost like the first day of class, like there's not much point in computing these things by hand, because part for that it's like the computer that you have. It's more like, question could be more like, oh, why would you apply the bisection method here? Or why wouldn't you apply the bisection method here? Or like things of that sort of like, making sure like you understand what the different methods are for, you know, but yeah, just take a look at the study guide because there I tell you which formulas I expect you to remember or which proofs. Like for example, I think I mentioned this one, like that if you have a contraction on an interval, then a function that's a contraction on an interval, then it has only one at most one fixed point. That's something we worked in class. So definitely, if you go through the notes, you can like see all the theory that's needed. But yeah, like for the exam, it's more like me just checking that you know what the terminology is, like what the different methods are saying. Because in practice, you never compute things by hand. So like, I just want to make sure that you understand the hypothesis of like, when are you allowed to use this, when are you not allowed to use this, and so on, for example, like if the function is not continuous, you cannot apply the bisection method, right? That sort of thing. I want you to kind of like understand the limitations. So I posted kind of like a practice exam. That was more or less based on like the number of questions and all of that is completely unrelated to the ones that I would have on the exam. It's just like an exam that I took from the summer when I taught it in the summer. I added some extra questions, but that one was still a little bit more like on the computational side. So I did add some extra ones so that it would feel more like a theoretical thing. But then I'll send you an announcement. To kind of like tell you on which of these PDF of problems for you to focus on. So I'll let you. I'll probably do like a final update to the list today or tomorrow and tell you. Oh, by the way, for the exam, you can pay attention to those as well. Yeah.
The exam's next Thursday.
Correct. Yeah, but we'll finish the material for today because this is kind of like a very nice like stopping point. Because with that way we wrap up all the polynomial stuff. But yeah, so like you would have like it's still kind of like a week and a half ish. Yeah. Well, I should like depending on how we're doing with time, I guess well, it would be more on Tuesday, I suppose, right? Of next week, right? Where yeah, I may stop a bit earlier and be like just to make sure if there are any questions or whatever. But yeah, I don't think I'm being a bit cynical, but I feel like until the weekend, people really start studying for the exams. So like doing reviewing here on Thursday, like it would not be worth it. And also the way it also gives me a little bit more of the time to update the list of problems. If I wanted to add something else, I wouldn't add anything else past this Thursday, but if I wanted to add something else, so that at least you have the weekend to review it and everything, Yeah. But yeah, just look at that. I'm recording this class because like I had not done this like during the summer, like this topic, but then realized, oh my God, this is such a useful topic. So I felt bad like not to put it like before. Yeah, yeah. So I'll upload this video to like the YouTube playlist for numerical analysis. Yeah. Were you going to ask me something? Okay, good. Yeah, yes. Because I thought, oh, this is such a like elegant way, and maybe like last in the summer I did. Oh, that's actually a good point. In the summer I did the splines, which is still interesting. So if someone wants to learn about splines, that is a lot used a lot for computer graphics and other things. Uh, it's kind of like a form of polynomial interpolation. It's just that you kind of like instead of like using something of very high degree, you kind of like say, oh, I want to approximate this by cubic polynomials, but then you kind of like do a cubic polynomial on one interval, followed by a cubic polynomial on another interval, followed by a cubic polynomial. So it's kind of like a piecewise polynomial thing. So if someone wants to learn more about that, like for example, you can watch the videos on the splines. But I felt like, kind of like you have to go into a lot of detail to kind of explain why those are useful constructions. I mean, they are, but like, it's much of a detour. And I felt like this connects a little bit better when we talk about ODEs and other things, because now I'm introducing the finite differences, which is what you need to do when you discretize an ODE. So I felt like I'll just do it this way, or just talk about this instead. Uh, because of the applications to differential equations that we want to do towards the end of the course. So yeah, just to go back to the problem. So Z0 we already knew was f of x0, and C1 is this divided difference, right? So let me just move some things around. So yeah, let's put it here. Okay, so it's f of x0 plus the first divided difference, right? F of x0 comma x1 times x minus x0. Okay, and as you can imagine, if you wanted to find the next value, the next coefficient, it would be C2, right? So we already plugged it at x0, we already evaluated at x1, so the next one would be to evaluate it at x2, right? So now you evaluate this at x2. Okay, what do you get? You get P2 of x2, right? Pn, sorry, Pn of x2 is the same as f of x0 plus f of x0 comma x1 times x2 minus x0 plus C2. Let's see if I can fit all of this into a single line. Plus C2, oops. X2 minus x0 times x2 minus x1, right? Because all the other terms you can see here contains an x minus x2. So when you plug in x equals x2, they go away, right? Okay, so now it's just solve. I mean, of course, I could just solve this already for C2 straightforwardly, but I want to present it in a way that, makes it clear what the recursive structure is. So again, just as before, because this polynomial is supposed to interpolate through x2, right? Like Pn of x2 would just be f of x2. So you get here. Okay. F of x2, right? And then I'll do, okay, just to kind of like do it in the way that is easiest, at least that I found easiest to explain how to find the formula. I'll also subtract, what do I need to subtract? I'll subtract f of x1 to both sides of the equation. So I'll subtract f of x1 to both sides. Okay. So I'll put it in green so that you see that it is being the same term that is being added. And you'll see why in a moment. It's kind of like a convenient thing. And then I'll copy paste the rest as this being the same. Let's see. Oh, I need more space. Oh my God. Yeah. Okay. Let me see if I can fit this all in here. And again, like just to kind of like write down the formula for the divided difference, I'll write it with A and B so that it's not biased because I'll use it a couple of times. So f of A comma B is f of B minus f of A over B minus A. That's how you should think about the divided difference. Another way to think about this formula, if you multiply by B minus A, right, is that the divided difference times the interval, right? Or the difference in the values is the same as f of B minus f of A. It's kind of like this, like kind of like saying delta f is the slope times delta x, right, or something like that. So both versions are useful, but this one, having it without the denominators, it's a little bit more convenient for me because right now there's nothing as in a fraction, right? So f of x2 minus f of x1, I can write it as a divided difference of x1 with x2. Let me write it this way. So I'll write it as how do I want to write this? Let's see. Okay, so I'll write it as the divided difference. Let's see, hopefully this works. So it will be the divided difference of x1 with x2 times x2 minus x1. Right, is that making sense? It's f of b minus f. Yes, that's fine. Right, because if you evaluate this, it will be f of x2 minus f of x1 divided by x2 minus x1, so it cancels, the x2 minus x1s cancel. Okay. And then let me factor a minus sign for the first two terms. So I'll write it as f of x1 minus f of x0. And I'll do something similar to this one, right? Where I'll replace it with a divided difference, but just to kind of like maybe do like an extra step. And then I'll copy paste this. Let's see, can I shrink? Oh, I think still fine. Let me just make this a little bit smaller. Is that okay? So far, so good. Does that make sense? Okay. So we're almost there. Like, let me just, again, you have to be clever because you can solve very easily for C2 in this equation. You just have to present it in a way that kind of like the structure is more clear. So that's where like some cleverness is needed because, why would you think about adding or subtracting f of x1 to both sides, right? Like, that's kind of like a convenient thing to do, but it's not super obvious all the time, right? So then I apply the divided difference formula here. So this would be minus f of x0 comma x1 times the length or the distance between the points x1 minus x0, well, or like, not the distance because it may not be positive, but like just the length. And then the rest is the same. The rest is the same. Okay. So what I'll do in the next step is just, I can factor out this divided difference. So factor out there. So and something fun happens. So you'll see in a moment. So let me factor this one out. So if you factor it, you get f of x0, x1, right? Okay, so there is a minus here, right? There's a minus here, so it becomes negative x1 plus x0, right? When you include, when you're factoring, it becomes negative x1 plus x0. And the other one is plus x2 minus x0. And then the last one is C2, x2 minus x0, x2 minus x1. And I don't know if you noticed something, there's a cancellation now that I can do, right? Because this one is x2 minus x1. There's an x2 minus x1 here. And after you cancel out the x zeros, there's an x2 minus x1 there as well. So everyone had an x2 minus x1. That's why you had to do this trick about subtracting the x1 on both sides. So let me cross them out like in a subtle way. This one goes with this one. Oops, no. Oh my God, this autocorrect. Sometimes it's very annoying. This AI thing. Okay. Boop. And there you go. So all the x2 minus x1s go away. And now we're almost at the, and you'll see it's very elegant. You're almost at the point where you see the formula. So f of x1, x comma, the divided difference of x1 with x2 is the same as the divided difference of x0 with x1 plus C2 x2 minus x0. Oh, okay, and then let's just solve for C2. So if you solve for C2 here, what do you get? You get f of x1 comma the divided difference of x1 x2 minus the divided difference of x0 with x1 over x2 minus x0. So it's almost like it's kind of like a divided difference of a divided difference, right? It's kind of like a difference of differences, right? Which is very nice. So these, it's like a higher order divided difference, and this is called f of x0 comma x1 comma x2. So this is defined as, so instead of calling it C2, because that number, the name is not, very, very informative, you divide this quantity as f of x0 comma x1 comma x2. Okay. So it's very, and you kind of like maybe start seeing, oh, maybe the next one would be a divided difference of this higher order divided differences. And that is more or less what happens. So I'll kind of write down what's supposed to happen. But I'll just say a couple of things extra about this one. So this is something that, this one is a little bit more of a tedious calculation, but it's still the case that it is permutation invariant or like is sensitive to the order, meaning that if you kind of like start switching around like the order in which you write these elements, that still gives you the same. So how many ways can you permute three elements? 3 times 2 times 1, right? Like there's 6 possibilities, like combinatorially speaking. So there's obviously like a more elegant way to prove this, but you can also do it by brute force. So if you want like a brute force calculation, if you want, you can check. Not too bad to check that, that it doesn't really matter in which order you list them. So f of x0, x1, x2 is the same as f of x0, x2, x1, which is the same as f of x1, x0, x2, which is the same as f of x1, x2, x0, which is the same as f of x2, x0, x1, which is the same as f of x2, x1, x0. So really, these divided differences or the higher order divided differences, they will always be insensitive to the order in which you list them, which is very nice, very important, very useful information. So the ordering of the elements. So it doesn't matter how you list, doesn't matter. How you list the three elements of the elements in this divided difference. And the other thing, well, here you have to be a bit more careful because you can kind of like take a limit, like, just kind of like as a sanity check. It is possible to show that if you were to take a limit where x1 and x2 approach x0, you get the second derivative of the function at x0 divided by 2 factorial, which is like kind of like the same thing that appears in the second in the Taylor degree, right? So, and it's also possible to check kind of some. I mean, that's not important for us. It's kind of like more like as a theoretical understanding. You can check that kind of like a limit as like, x2 x approaches x0 and x1 approaches x0 of this divided difference is well, it makes sense that it would involve the second derivative because this is kind of like a difference of differences. And what is a second derivative? It's a derivative of a derivative. So in that sense, it's kind of like plausible that this would be related to the second derivative of the function. And then the factor of 2, well, you have to think about that a little bit more, like, maybe like it would come from some sort of L'Hopital's argument and something like that. But, so all that I want to emphasize is that this is kind of like really extending Taylor's formula to the case where you're using separate points, so this higher order divided difference is a finite version of the second derivative. That's how you should think about this. So f of x0, x1, x2 is kind of like an approximation to the second derivative in a sense. And again, that will be a useful idea when we talk about differential equations, because when you have a differential equation, if you want to use a numerical method to solve it, you want to approximate the derivative with a finite version of it. So you can use like the finite, like this divided differences. Is that okay? Is that making sense? And I don't know, I find it very elegant. Okay, and now I think we're ready. I can finally tell you the formula for the rest. So it is always a difference of high order finite differences, essentially. So it's what happens, and again, there are many ways to check this, induction and other ways, but let me see where I have it in general. So one can check. Again, it's more like to appreciate, like, the idea of it because it's very elegant. So one can check that what I'm calling CK, the kth coefficient. Let's see. So essentially, you delete one of the, factors, right? And well, because this is going to be called, as you can imagine, this will be called f of x0 up to xk. So ck equals, let me put it like this, ck is going to be, the name that I'm going to give to this is f of x0, x1, x2 up to xk. But what is that? That is just, you delete the first factor, you get a divided difference. You delete the last factor, you get a divided difference, or higher order divided difference, right? So you take the difference of those higher order divided divided differences and then divide by x k minus x0. So it's kind of like it is really like a very elegant formula, and you can kind of like see that it does have like this recursive feeling because like to compute this third order or fifth order high order divided differences, you need the fourth ones, the third ones, in the same way in which to find the fifth derivative, you need the third or the fourth derivative. So it's kind of like all like builds up on itself. And it is possible to check, yeah, that if you take a limit as all the values approach x0, you get like the kth derivative at x0 divided by k factorial. So you can also check, it is possible to prove, kind of like you can prove that kind of like the limit when x1 approaches x0, x2 approaches x0, xk approaches x0, that the limit of this higher order divided difference is this like the kth derivative at x0 over k factorial. So they are a generalization of like the higher order derivatives essentially, which is very nice. So is that okay? Is that making sense? Okay, so the last thing that I'll do is kind of like give you like an error formula that we have everything in place for that. So again, in the context of how we're thinking about the problem, we were doing sampling, meaning that you had this function f of x, you choose like maybe 10,000 points, a million points, and you just keep a million points of that function, like, of the values of the function, right? So you might ask, in general, how far is f, what is f of x minus Pn of x, right? When x is completely arbitrary, when x is not one of these sampling points, right? Um, so the trick is to kind of like imagine that, like, let's just focus your kind of like the attention is like so originally we had x0 f of x0, x1 f of x1, right, up to xn f of xn. Those were like the points that we started with. Just imagine adding an extra point to this list. Let's just say that you have an extra data point, which I'll just call x star, just to call it, not call it x because it's too confusing if I call it x. So let's just add an extra data point. X star f of x star to this list. Right? Because now you have an extra point, right? Now there is a polynomial of 1 degree higher that passes through the previous points together with the new one, right? So there's a new polynomial that passes through the original points plus its new point, right? There is a new polynomial that passes through the original points, through the old points, plus this new one. It has one higher degree. It is 1 degree higher, right? So I'll just call it Pn, let's call it Pn, I'll call this polynomial Pn, Pn plus 1. right? Because it has 1 degree higher than before. Okay, but because of the recursive nature, that's the beauty of the Newton form. Because of the recursive nature of these polynomials, or like of writing them in this way, this polynomial of 1 degree higher is the previous polynomial plus the x, the new factor, right? So that's the beauty of like of the method, you know. So this is the same. You know, it's the previous polynomial plus the new factor. The new factor would be, you know, this divided difference times all like the product of all these things. So right in the degree n polynomial, you end up at x minus xn minus 1 because this has 1 higher degree. That's not why you end up to xn. Okay. And then if you evaluate this equation at x star, right? This is this value for every x. So if you evaluate this at x star, you know, so what? You know, take x equals x star, you get Pn plus 1 of x star, right? You get a Pn plus 1 of x star is Pn of x star plus all this stuff. But what is Pn plus 1 of x star? Well, it's supposed to interpolate through this point as well. So that's just f of x star. So you end up getting that f of x star so you get that f of x star is Pn of x star plus this divided difference. Okay. But X star could have been whatever in the world. Like they didn't give it a, you know, it's nothing specific, you know. I just call it X star for psychological purposes. So call X star X again. If you call X star X again, because why not? You know, you get like a formula that f of x is Pn of x plus disjunct term. And so this is kind of like the, you know, similar to this error term in the Taylor polynomial. So call X star X again. And so you get the f of x equals Pn of x plus f of x0, x1, unto xn, x star. Sorry, now x is x star. You get this. Sorry, this could be. And that essentially tells you how much, you know, that tells you how different f is from the polynomial, f of x minus Pn of x. So the difference in the error, right? What is an error? You know, an error in and that's the last thing I'll write for today. What is an error? The error is the absolute value of f of x minus the polynomial, right? So that is just so basically it is the absolute value. It is controlled by the absolute value of this divided difference times the product of these factors. And there's a way, I think I wrote it on the study guide, and we're not going to use it, but there is a way to write this divided difference using the mean value theorem as the n+1 derivative, kind of like similar as in the Taylor polynomial case. You can write it in terms of an n+1 derivative of a point that is somewhere between these points. But it is less important, just to appreciate the formula, which is kind of like, the point is that of this formula is that it gives you a precise estimate of, if you have, just to summarize, you start with a random function, you choose a number of points, right? Some like maybe 10,000 points, a million points out of this function. You create a polynomial that approximates the function with those million points. How much does the polynomial differ from the function? Is given in terms of the divided difference of the function times this like product of factors. So the important thing is that it is a concrete thing that in principle you can control if you can control the product of these factors and if you can control the divided differences. And that's kind of like the point of like appreciating the formula. So yeah, let's finish for here today. And then, yeah, on Tuesday, we'll talk about a slightly different problem, which is how do you find a polynomial that approximate a function, but now it's not passing through the points. You just want to minimize the error so that we'll get into these squares. But for that, we have to talk about kind of like an dot product for functions, which is called like an inner product and orthogonality of functions and other things like that. So it's a good place to end, I think.